There it is. Okay, I'm very happy to be here. Thanks for the invitation, David, and it's really a pleasure to be here. I'm spending what I'm calling a mini sabbatical over in Stockholm for 6 weeks at the Stockholm Resilience Center. And I'm at the end of my sabbatical because I've spent the last better part of this past year getting this project going. And I'm going to talk indeed about this new project. All of the logos that you see are the various institutions that are involved in the project. And so I'll sort of come to that at the end of my talk of what we're doing in that project. But before that, just sort of set up basically what we're trying to do. Let me turn this on so we can walk around. So. So it's probably not news to anyone here that we are in this era of accelerating change, and that change is brought about by various human activities that have shown really dramatic increases in particularly the last 50 years. So things like, I don't know, there's some of these things that are pretty funny, like McDonald's restaurants and motor vehicles on the road and so forth. But all of those changes in human activity have led to changes in the environment. And one of the most dramatic of those changes is the increase in atmospheric carbon dioxide, which of course is changing our climate. But one of the things that happens with climate change is not just that temperature goes up, but also that we're seeing an increase in the frequency and severity of extreme events. And this is a chart from Munich Re, and the reinsurance industry has to keep very, very close tabs on what's happening with extreme events, and they do. So you can see in this chart between 1980 and about 2014, the increases in extreme events that have happened worldwide, and all except for the red part of those bars are extreme events that are weather-related, so potentially related to climate. But whatever their cause, extreme events are increasing, and we expect them to increase in the future. And cities in particular, because of the places that they're located, many times along rivers, along coastlines, and so forth, but also because of the concentration of people and infrastructure in cities, are particularly vulnerable to these extreme events. So at the same time that the climate is changing, environmental change is occurring, the world is also urbanizing. And this is a map of an image of nighttime lights. We already know that half of our population on Earth lives in cities, and that number or percentage is expected to go up to 3/4 or 2/3 by mid-century, possibly up to as much as 80% by the end of the century. And most of the population growth that we're seeing on Earth is urban, so that by the mid-century, when we increase the number of urban residents, that number will exceed the number of people on Earth now, the number increase in that population. And in fact, in many areas, very fast-growing cities are springing up in parts of the global south in particular, where the extreme rapidity of growth is really presenting a challenge in terms of keeping up with producing enough infrastructure to meet the needs of these expanding populations. So cities actually interact with a variety of types of global change in a variety of ways. They interact both as drivers of change and as responders to change. And so this is a graphic that came from sort of a conceptual framework that came from a paper that my colleagues and I published now 8 years ago, in which we argued that cities really drive a lot of the kinds of changes that we're seeing in such things as the climate, biogeochemical cycles, hydrology, biodiversity, and so forth. And in the case of climate change, we know that the emissions of carbon from cities are responsible for probably around 70% of the global emissions of carbon dioxide. And yet maybe even more than that, because cities are so dependent on external ecosystems. So the demand from cities for activities such as extractive activities and the rest of the landscape can drive that number even higher. But what I want to focus on here is really how the cities sitting at the local scale there, and cities are local phenomena that are widely distributed, how cities are potentially also responding to climate change, in particular because of the increase in extreme events. So the challenge here is that urbanization and climate change are on a collision course. And we believe that the battlefield where this collision course is going to be played out is in terms of infrastructure. Now, when I say infrastructure, I'm going to be talking about infrastructure in a way that maybe is not what you all expect. I think of infrastructure as including elements of biological or ecological systems, elements of the social system, and elements of technological systems. So social, ecological, technological systems. So cities are actually uniquely characterized by their infrastructure. And I think that infrastructure can sometimes present challenges in the face of these extreme events, but sometimes opportunities. So just for an example here, I'm going to talk about these extreme events and their distribution. This is a map of cities over 750,000 in population and the distribution around the world. And you can see the color refers to the hazard deciles of urban flooding as a global challenge as predicted for 2025. And this is done by the UN Population Division in 2011. And you can see that there's a distribution. So some places are expected to see less hazard and other places to see more hazard. The risk of flood for the world's cities is highest in places like China and India and low-lying coastal areas in North and South America and Europe. So here's where I'm from, right there, southwestern United States. And that has a pretty low chance or a pretty low hazard risk for flooding. And yet here's what happened in September of 2014 in Phoenix metro area, where 10 to 15 centimeters of rain fell in less than 24 hours. This is in an area where about 20 centimeters of rain is the average annual rainfall for the region. Okay, so we're talking about almost the entire annual rainfall, or over half the annual rainfall in a single day. And it resulted in things like, that's an interstate highway there, flooded in Phoenix. And the upper left is a neighborhood in Mesa, Arizona, which is one of the cities in the metro area. And this is a wash that some unsuspecting soul tried to cross in his car and ended up being impaled on a branch. So when we think about an event like this, I think the point that I want to make is if we look at history, if we look at history in terms of flooding, we can plot this out in terms of what's called a depth duration curve. So that amount of rainfall over that period of time, and how frequently would that occur? The different color lines are the frequency or the recurrence interval for that kind of event. And if we plot that September 8th event, it comes out being more than once every 1,000 years, so a very low probability event. But I think the important point here isn't that that was a really big event, it's that we don't really know what the probabilities are. We're living in a world where the probability of a given event is changing all the time. And so we can't really use those methods that we used in the past, which is to examine what happened in the past and what the probability is, and use that to plan our infrastructure and so forth. Another example, water scarcity. This is the same kind of analysis. And again, you see a distribution, a particular distribution with not what you might expect in terms of water scarcity and the distribution. And I happen to live in a region where water scarcity is a problem. But one of the cities in our network is Portland, Oregon. And here's Portland, not thought to be an area that will have a very great probability of this hazard. this is what we think of when we think of Portland. It's a very green place. It's green because it rains all the time. But this is what happened last year. In June of 2015, the Pacific Northwest in the United States was in very severe drought. This was before California really went bonkers, but essentially with drought and heat waves and these kinds of events that we wouldn't expect in this environment. And so I think that the point that I want to make here is that these kinds of extreme events are what we might think of as the new normal. The new normal is something totally different. There was a recent paper that came out that suggested that events that occurred on average once every 500 years in New York, these are storm surges, are now occurring on average every 25 years. So these are really different times, right? These kinds of extreme events have obvious impacts locally. They also impact cities because they can have effects on supply chains to cities. As I've said before, cities are dependent upon external systems. We certainly know that there's social and political strain from the impacts of extreme events. Just think about water scarcity and drought as an extreme event and how that has arguably resulted in a lot of social strain. And so the thing we're thinking about this is when we think about the solutions, we can't use the methods and the ideas that we used in the past. We have to think about solutions that are flexible and that account for this uncertain future that we don't know, the probabilities that we don't really know. And I'm arguing, our group is arguing, that the kinds of solutions that we are thinking about need to incorporate not just the technological angles, but social and ecological elements as well. So I'm going to go through a couple of examples just for touching on the kinds of extreme events that have occurred and then what some solutions that I'm talking about, this kind of solution that I'm talking about, might be. Now, extreme heat is one of the big challenges in terms of extreme events because it really does kill people. And people in Europe know this from the 2003 heat wave that resulted in over 50,000 excess deaths. There's some other information here. For example, we see increases in sort of related, not direct heat impacts, but related health impacts of extreme heat. In Phoenix, we have approximately 100 deaths per year that are related either to direct or indirect heat events. And in the future, we should expect to see this to an even greater extent. This is actually from the U.S. National Climate Assessment, showing under different scenarios the number of days over 38 degrees C, 100 degrees Fahrenheit, under different scenarios for mid-century, or actually for different time periods. So this would be 2021, 2040 to 2070, and 2070 to 2099. And look at the Southwest. I mean, it looks pretty scary. It looks like we can expect to have a number of days that are these what we call misery days in the future under higher emissions scenario, which is incidentally the trajectory that we're on. So we would expect more heat waves and fewer cold waves, and possibly more humid heat waves, which are more miserable than dry heat waves. But here's a thing to note, and this is just hearkening back to this cities as drivers and responders, is cities also sort of modify their local environment. So the people that live in urban areas already are experiencing heat, extreme heat, and increases in heat through what's known as the urban heat island effect. And so we're pretty sure we can attribute most of the change that you see between 1900 and 2010 in this graph for the Phoenix area to the urban heat island. So increases in the number of misery days, that's the number of days over 100 degrees Fahrenheit, or 38 degrees C, and almost a complete loss of frost days. So already we're seeing these kinds of events happening. This is just another projection this is an index that's developed so that multiplies extreme heat days times the number of parcels affected, so it gives us a little bit more of an index of the extent of heat waves likely to affect these two cities in the future. And here's a really important element of heat waves, and that is their effect on people. So this is studies coming from the Central Arizona Phoenix LTER that David mentioned that I've been directing. This is the work of Ben Riddell and Sharon Harlan and others. And this is just it's such an amazing finding. They did a study of a particular extreme heat event that lasted for 4 days. And here they've plotted different neighborhoods in the Phoenix metro area. The small dots experienced very low heat intensity, that is very few hours over some threshold of heat, and the big dots experienced very high ones. And you can see they range from 0. Neighborhood 2 has 0 hours of extreme heat. Neighborhood 1 had 24 hours of extreme heat in that 4-day period. But if we then look at and classify the neighborhoods according to their exposure, and then look at the characteristics of the people living in those neighborhoods, what we find is this environmental inequity, where a higher percentage of minority, a lower family income, and a higher percentage elderly occur in these areas that are exposed to more extreme heat. So how can we remedy this kind of situation? There's a very long story that I could get into that tells you why we ended up in this situation where the poor and ethnic minority neighborhoods tend to be more exposed to extreme heat. But potential solutions are, for example, this. This is just contrasting two neighborhoods that have a very low coverage of vegetation and one that has a very high coverage of vegetation. And that external vegetation can account for a great amount of differences among these different neighborhoods. There's a very strong correlation with outdoor vegetation. So there's a potential solution, the use of the urban forest or outdoor vegetation to ameliorate this extreme heat, which of course you're going to notice, because I'm talking about Phoenix, that it requires water. So we have to think about the trade-offs associated with the use of water to support that external vegetation. But I'll just leave that there for now. The second example I wanted to talk about was Hurricane or Superstorm Sandy, which occurred in New York City in 2012. New York City in the eastern coast, with sustained, very, very high sustained winds, $32 billion in damage. 53 people died. Thousands of homes were destroyed. And over 250,000 vehicles were destroyed. As you can see, this is the classic New York City yellow cab. A number of those were destroyed. So it was a really strong, very big event. And one of the things that is worrisome about these kind of storm surges associated with hurricanes is this. This is a number of extreme events that have occurred since 1950 in the New York City area. And this is the height above the mean low water level that these different storm surges achieved. This line here, the red line, sorry, I'm trying to point and it doesn't work with this screen. This red line here is the level at which the New York City subway floods. And you can see that in Sandy, it actually surpassed that level. But what's happening is that a greater fraction of this total storm surge is attributable to sea level rise since 1900. And then you have the storm surge, which is a really big part of it as well. So we have to think about these various factors all interacting in worsening the situation. So if we look, for example, for the New York area, we can look at the projected changes in floodplain. And I was just looking at this map out here, which is fantastic. That's been developed for the port area for Gothenburg, and it has pictures of what would happen at the 1 meter higher sea level. Very fantastic. But these are actually the Federal Emergency Management Agency, FEMA, their maps of the 100-year floodplain and how they expect it to change by 2050. And what we can do in these cases is this tells us about exposure, but then we need to know about vulnerability, and so we can actually map social vulnerability in terms of people that are what is their capacity to adapt to this? What is their ability to get out, and so forth? And in fact, in New York City, there's a really good examples of how people are beginning to work with nature to actually try to increase the defenses, the ecosystem-based defenses or nature-based solutions to these kinds of storm surges. In some areas that had leveled their sand dunes, housing was completely destroyed, so there are places where people are trying to revegetate the dunes, as you see here. This is a very large salt marsh restoration project that's been announced by the U.S. Fish and Wildlife Service. So those are two examples that just tell you sort of how we're beginning to think about solutions as having these elements. And these are the three elements I'm talking about, elements of the ecological, biophysical, the technological infrastructure, and the social behavioral domain. And I think what's true is that many people have worked on social technological systems or social ecological systems, but there's really been very little work that's trying to bring all three of those domains together. And this is what we're doing in our project. Our main questions that we're asking is how do these sets domains interact to generate vulnerability or resilience to climate-related extreme events? So that's the basic science question that we're asking. And the second question, which is more of the action question, the knowledge to action question, is how can we guide the dynamics of these social, ecological, technological systems along more resilient, equitable, and sustainable trajectories. So this is the part of the project where we get involved with local governments and with actually designing new projects and so forth. So these are the ideas that we're pursuing in this project. It's called the Urban Resilience to Extremes Sustainability Research Network, otherwise known as UREX, which sounds like a medicine, I think. In our project, we're focusing on 4 types of extreme events: coastal flooding, extreme heat, drought, and urban flooding. And these are the cities that we started with. We're trying to add cities to this network, looking for partnerships. So we've talked to folks in La Habana in Cuba and in Santo Domingo in the Dominican Republic. We have added Mexico City since the project began. Anyway, those are the cities that we're working on. Oops, I'm sorry, I missed one. And we also recognize that those 4 events interact with each other, and they also interact with other kinds of events. So this is an example. Miami, which actually is just announced as one of the new Rockefeller cohort of 100 resilient cities. Miami is an interesting case, Miami Beach in particular, because they're getting almost daily flooding from tidal flooding that's associated with sea level rise. And so you put those together with the kinds of coastal storm surges that I'm talking about, and it could be pretty severe. The approach that Miami is using is called rising above. They're actually trying to levitate the city and build up the streets and so forth. It's a question how long that will last, but there you go. Bolivia is one of our cities. This is a very small city in Chile. It's one distinction or reason that people may know of it is that it is near the epicenter of the largest earthquake ever recorded. This was an earthquake that was 9.6, I believe it was. It was a massive earthquake. The tsunami that resulted from it leveled Hilo, Hawaii in 1960. But one of the things that happened locally in this environment was a 250% increase in wetlands. And so now they have this city that is dominated by wetlands that weren't there before 1960. And so the real challenge is how do we actually work with these wetlands rather than trying to fill them in and rebuild the city the way that it was before. Okay, so in face of these kinds of events, there has been decades, centuries of research on disaster risk reduction. And an approach that says, okay, this is from the Intergovernmental Panel on Climate Change, but it says that impacts or the risk sort of lies at the intersection of these natural processes like climate variability, anthropogenic climate change, and socioeconomic processes that generate vulnerability and exposure. And it's a reasonable approach, but we think that that sort of understanding the hazards or the probability of or likelihood of failure is challenged in this kind of approach, and that a better approach is one that recognizes the possibility that systems can transform, that a system could move beyond the state that it is and move into some sort of different state. And so we're using this framework of resilience, which is actually one of the reasons that I'm here in Sweden this year, is to think about, as the Royal Society put it in the project that I worked on, as resilience as having this possibility of moving beyond adapting to extreme events to actually transforming. We're using the Rockefeller Foundation's definitions because they're very simple to understand. The capacity of individuals, communities, and systems to survive, adapt, and grow in the face of stress and shocks, and even transform when conditions require it. So the qualities of these systems are some of these things I've been talking about. The idea of reflectiveness, of looking back at what's worked and what hasn't. The idea of redundancy, of flexibility, of integration. And here we're talking about integrating these three different components of these three different domains that I mentioned earlier, and the diagram is over there. And so this is a work in progress. This is sort of where some ideas that we're heading on developing this framework of resilience for cities in the face of extreme events, and this resilient infrastructure that we want to imagine. It's going to have a variety of inputs that need to feed into that infrastructure. So these are going to be the technological, the ecological, and the social elements that will feed into that infrastructure. That infrastructure will provide services. We already expect something like a seawall to provide the service of protecting us from storm surge. But, and so that's sort of the single service that you might expect from the technological element. But maybe we could also capture some ecosystem services, for example, by regrowing fringing marshlands in coastal areas. Jobs created and maintained is one of the services provided. And then there are a variety of outcomes, and it's the sort of recycling of this whole thing that allows the system to transform. So if there's something that totally changes, then you have a new system state that can continue the cycle. So this is a work in progress. It's the beginning of what we're trying to do to think about what resilient infrastructure has to look like. What are components of infrastructure that is resilient? Now, these ideas are definitely not new to us. They have been developed in a variety of other ways, but if we think about, these are a variety of infrastructure solutions that all have elements of ecological systems in them. This is in Arizona in the upper left. That's a retention basin. It's used as a place to absorb water, stormwater. This is a combination, what I would call a hybrid solution, a combination of the sort of structural material and the marshland growing behind it. A green roof is obviously a combination or hybrid sort of system. This is a curb cut that is absorbing stormwater in a street in Portland, Oregon, and I've mentioned those others as well. And so we can really think of this infrastructure as lying along some sort of a continuum from gray to green with hybrids in the middle. And yeah. So these ideas also have been part of this report that came out in 2014. This is available on the web if you're interested in it. And this was done by a group with the Royal Society looking for what is the resilience, how can we characterize the resilience to extreme weather. It wasn't completely urban focused, but there was some urban work that was done in it. And so the question is really, can we think of things like this mangrove forest here as potentially nature-based solutions that can help us to protect against coastal storms in that case? And so one of the things we did was we gathered evidence from the worldwide and then evaluated solutions of various types, and this is to coastal flooding. And these graphs are interesting. They're complicated, but I think it's kind of a nice way to express it. We've plotted the effectiveness of a solution against its affordability. So effectiveness is, and then the color coding refers to whether it's an ecosystem-based hybrid or engineering solution, and the strength of the evidence is the thickness of the ring. And then you have a plus, a minus, or nothing with respect to the co-benefits or additional consequences that might exist from that particular solution. It's interesting that for most of the things we looked at, they had this shape. So gray on the left, more effective, less affordable. Lots of evidence. Green on the right, a little bit less effective, much more affordable, and variable evidence, but often with co-benefits. And you can see the numbers there refer to the various kinds of solutions. So for instance, if we look at beach and dune nourishment, it's up here. That's sort of a hybrid solution and is pretty effective. Here's one for heat waves, not as many. And the big winner here is most effective and most expensive is air conditioning. And, it was just yesterday was quite warm here, wasn't it? And you think, what if we had a heat wave here? I mean, there's no air conditioning. This is it's really it's an absolute essential element of living in Phoenix, Arizona. So one of the vulnerabilities of that infrastructure is that it is dependent upon the delivery of an energy supply to keep that running. So a heat wave combined with a power outage could be a very, very serious issue for a place like Phoenix. Okay, so we're contrasting these traditional solutions, which are what you might call fail-safe, with a resilient solution that's what you might call safe to fail. So a fail-safe solution is one that has a very low probability of, it's guarding against the low likelihood events that have very high consequences. And it usually is associated with highly modified infrastructure. This is a great example here. I work on streams, so a lot of my examples end up being streams. A resilient solution, on the other hand, allows more frequent failure. It may be more flexible and multifunctional, but the consequences are going to be smaller. And the example that I'm using here, I'll show you a little bit more about this, is in Scottsdale, Arizona, this green belt that was built in the 1970s. This is called Indian Bend Wash, and this is an aerial photograph from 1935. You can see it was mostly farmland in 1935, and this ephemeral stream that flows through this farmland has been left pretty much alone. It's fairly wide. It doesn't have perennial flow in it, but when it floods, it fills up that floodplain. And so the farmers pretty much left that alone. But once development started to occur, the land is valuable. They started to encroach on the stream. And there were a series of pretty severe flood events that occurred in the late 1960s. And as a result of that, there was a proposal to actually build a concrete flume, an LA River-like thing, through Scottsdale. But there was an organized community, so here's where the people come in, that said, no, we don't want that. They voted it down. And instead, they advocated for this greenway to be built. And here is what it looks like today. That's exactly the same spot. You can see that it's highly urbanized, so there's a lot of housing. This is sort of Phoenix-style urbanization, which looks like suburbia. But we have this green belts, which is a series of parks and ponds connected by little streams. Here you can see an oblique view over here. And what happens when it floods is that, well, things move around a little bit, but nothing really gets harmed that much. It provides also the ecosystem services of recreation and enjoyment of nature. It also, actually, we found, has this added benefit of allowing for nitrogen removal through the process of denitrification. That's a whole other seminar. But here it is with water in it. And so you can see the whole thing sort of fills up, and the lakes just become part of the stream. Some of the low water crossings get closed, and water just flows over those. And when it's done, they have picnic tables and garbage cans that are chained down to the ground, and they just set those up again and rake the leaves, and they're done. So it's really pretty simple. So I think, my arguments, when I give this talk, I often talk to people who work in social ecological systems, and I say, yeah, that's great. We've been doing that for years. We've been working on trying to bring together the social sciences and the ecological sciences to understand these systems that are very human-dominated. But I think that in cities, we absolutely need to also bring in the engineers. So we really need to start much more of a courtship with engineers as well as designers and others to have a better understanding of what kinds of solutions might work. Okay, so these aren't, again, only my ideas. This is actually a chart that I've adapted from a paper that was written by some engineering colleagues, and Tom Seeger is the one I was talking to, and he said, "Oh, you should look at this paper that I've written." And what I found to be quite interesting there was they're contrasting a sort of classical risk management approach with a ecological resilience approach, which is the thing that we're kind of advocating here. And it's the fail-safe and the safe-to-fail. And really what they're arguing, and I think is true, is that we need to move from this idea that we're whatever we put up is going to not fail. We're not going to let it fail. It's going to have to be big enough that it can take whatever the next storm surge is going to be. It's going to have to be the gigantic seawall that we have to live behind all the rest of the time. And instead of that, saying, well, okay, we know that we don't know what those hazards are, but we're going to try to design a solution that allows for some failure that has sort of less consequence. Okay, so minimizing the consequences of failure, but allowing frequent failure. And the strategies are going to involve a lot more of these sort of resilience concepts like diversity, adaptability, flexibility, innovation, and so forth. I mean, why not, if we build something, some infrastructure, why not say, let's put this in. Let's see how it goes. Let's monitor it. And if it isn't working, let's modify it. So the idea is to actually try to use more of an experimental approach, more of a flexible and reflective approach. Okay, so a little bit more on this project. As I said, we have 10 cities now. We have 17 institutions involved in this, some over 90 participants, and also 95 practitioners. Those are the people we're working with in each one of the cities. So they're city managers or city sustainability officers, or some of them are county officials. We have some NGOs like Nature Conservancy Partners and so forth. We're just almost 1 year, not quite 1 year into this project, and starting in the fall, we'll have 15 graduate fellows starting with us and 8 postdocs. Not been with us this first year, so I'm very excited about that. And we're organized across these cities into these working groups. And the idea is that each city researcher team has ecologists, social scientists, and engineers. So we're not putting all the engineers in one place and the social scientists in another place and the ecologists in another place. We're all trying to get together in all of the cities and across all of these working groups. So very briefly, the idea is we have these city teams that work with the city practitioners, and they also feed into this group that says, what can we learn by comparing across the cities in terms of what what has worked and what hasn't worked. So the city comparisons and city teams are doing that. We have a climate and hydrologist team that's actually downscaling climate models to try to apply them to each of our regions and develop hydrologic models to project extremes that are likely to happen in those regions. We have this group that's further developing these concepts of sets resilience, resilient sets infrastructure. It's a sort of more of a conceptual group. And then we have a group that's developing visualizations based on these projections and what we know about the cities. And then these, I think, are really the meat of the project. So the idea is that we have a group that is planning and working with each of the cities to do some visioning of future scenarios for those cities and how they can be adaptable or how they can actually become resilient to the extreme events that they're experiencing. And then another group that's actually trying to work with the cities to implement some projects on the ground. So those things are very exciting. And yes. Okay, after this, I have just some very, very quick teasers about, we've been doing scenarios in Phoenix for about 2 years now, and we have some initial output that's pretty interesting, so I thought I would show you that. But this is sort of where we hope to be with this project. We're also very interested in linking up with other projects and networks worldwide. I think this will be a really great way, for example, through Future Earth, to bring together people that are doing similar kinds of things throughout the world. So it's one of the reasons why I was very happy to come and visit Mistra Urban Futures for this reason. So we want to be this network of collaborating interdisciplinary scientists and practitioners that are working to promote, design, and implement urban infrastructure that's resilient, but provides ecosystem services, improves social well-being, and exploits new technology. So we don't want to leave out any part of those three things. And we want to be sure that it's equitable, that it benefits everyone in the population. Okay, now just a very quick sort of what we're doing with these scenarios. This is a project that's called Sustainable Future Scenarios, been done by CAP LTER, and this is Phoenix. Just thought I'd throw a picture in there. But basically, we're using 3 different styles of envisioning, and 2 of these involve these workshops, like you see in the picture here. One of them is to say, given what the extreme events that are likely to be happening, what are some adaptive solutions that we can envision to that? And so that's the adaptive scenarios. Then we also have these scenarios that are really based on sitting down with people and saying, what do you envision? What do you want this? It's a very normative process. What do you want this city to look like? You know, what's it going to look like? And so you pick your desired outcomes, but then you backcast, where do you have to be in 2050 if you're going to be there by 2060? Where do you have to be in 2040, 2030, et cetera? And then we have this forecasting approach, which is really not done in the workshops. Basically, it's done by content analysis of city documents that say what they want to do. They say, we want to be this, we want to be that. And so we take those and we use their written words to develop these strategic scenarios. In the case of the 2 that are done in the workshops, we actually have 3 versions of each one. And so the process has involved a variety of steps. We're actually somewhere around here now, where we're looking at these modeled scenarios and indicators. And in this fall, we're planning to roll out the first version of these scenarios in a public event so people can comment on them and help us make them better and so forth. So here's the current state. This is 2015 and the different land covers that you see for the Phoenix metro area. The gray is urban, dark is high density, light is low density. Then we have various land covers and agriculture, canals, water, and so forth. So you just get a picture of that's what it looks like now. And here is one of the scenarios. This is what we call the adaptive drought scenario, or the true cost of water scenario. And this was developed in these workshops where people said, okay, in the face of drought projections that we see for this future, what does the city really need to look like? And you can see it's contracted a little bit. There's a lot more density in the urban center. So a lot of urban infill and increased density, rainwater and stormwater harvesting. These are just some of the characteristics of the scenario there. And we also are working with an artist. So if you sort of zoom into the star there, there's a little vignette of what you might see in this sort of adaptive drought scenario. So some of these features are rainwater harvest and roof gardens and various things like that. The second one, and this is out of 7 scenarios, I'm just showing you 2. I like this one, it's called the Emerald City, or the Emerald Necklace. And the idea is that there's a series of canals throughout Phoenix, and we're taking those canals, and every place they cross freeways, creating a sort of garden-like emerald. And so these are the hubs, and the freeways are repurposed, so they only have 1 lane or 2 lanes with high-speed buses and no cars. And that's the sort of picture that you get. So there's a lot of green in these sort of emerald necklaces. And here's the vignette, shows you that sort of idea of that greenness. And so we just finished, after developing these scenarios, we sort of fed the input to our modelers and have a couple of models that are shown here. But here's the adaptive drought one. And this is the 2060 projected regional temperature based on WRF modeling for that scenario. So you see that in this idea of preserving water, we've lost that ability of the vegetation to really cool the environment. So we have some pretty extreme heat that will occur in that area based on that scenario. And here's the emerald necklace, where you actually have a cooler kind of situation with only a few hotspots of red. So those are initial results from this, and we have a number of these, and it's pretty exciting because we can show these to people and sort of say, well, is this what you wanted? This is what you said you wanted. Is this in fact what you wanted? Okay. So that's it. I just go back over what I've told you. First of all, that global change and urbanization are representing a collision course or converging challenges, and that extreme events, we should expect to see more frequent and more severe extreme events. And these are the ways that people are going to experience climate change. They're not going to experience climate change as a 0.2 degree increase in global temperature. They're going to experience it as extreme events. I think that using a resilience-based sets framework, social, ecological, technological systems is a useful framework for thinking about this collision in this sort of non-stationary world, where we think about resilient infrastructure as providing ecosystem services, improving social well-being, also taking advantage of new technologies and being equitable. It should be appropriate to place, and this is one of the reasons that we use multiple cities, because the challenges in these different cities are not the same. And so we don't just develop one solution and say, that's going to go everywhere. It has to be appropriate to place. It should integrate across these 3 intellectual domains. It should be flexible, multifunctional, responsive, and so forth. And so this project that we're starting, or that we have started, is new research that is actually going to try to develop a knowledge attribute network of researchers and practitioners in 10 US and Latin cities. So I want to thank you very much for your attention, and I would really be interested in hearing your feedback and any thoughts that you might have about this presentation. Thanks.
Thanks, Nancy.